So, hello everyone. It's a pleasure to be here today with you. And I'm Pierre Walch. Pretty sure that everyone here already know me, but you might not know what I was doing during the last few years. So I will correct this by presenting you my thesis work on the study of high repetition rate laser filamentation for the development of a laser lighting rod. All this work was done in the framework of the project that is specifically called the Laser Lighting Rod Project. And it's a kind of project with a simple to understand goal, but hard to achieve. It is to control real lightning discharge with a process called laser filamentation for the development of a new type of lightning protection. This work was funded by the European Union, and it was led by us here at the CNRS, and involved many international partners like the University of Geneva, Schum Scientific Laser, Ariane Group, AMC, École Polytechnique Fédérale de Lausanne, and HESSO. Well, this is a project. But we can start to wonder about, first, there is a little more explanation about this project in a paper submitted and accepted last year. So what is a laser and how do you use it to guide lightning? Well, if you want to understand it, first, you will need a thundercloud that will create the so-called lightning. To this, you add first a tower that acts as a lightning rod. And to this tower, you add a laser system. You focus this laser system to the top of the tower, and you will create a plasma there. And the plasma will attract the lightning and act as a lightning rod. This idea is already quite old. It was already described in the 70s, like 10 years after we started using laser. And it's the kind of idea that makes people dream. Even in the 60s, there was a comic book that described how two detectives investigate near Massy Palaiso, a team of evil scientists that controls the weather and lighting using electromagnetic wave. I promise it's not us, and we're not evil. But just didn't stay just a work of fiction, because already in the 1995 in Japan, there was a real campaign trying to test how we can use a laser to guide lightning. With a setup really similar to the one I just shown, where they focus laser to the top of the tower to try to create a plasma. During their campaign, 2 lightning events only were recorded, and the main drawback is that the plasma length where they conducted lightning was only 2 meters. So for any application, it's quite an issue. So if we want to improve this setup, we need to discuss about a process called laser filamentation in air, which is a nonlinear process for high power laser that will result in the creation of a long plasma channel. This process was described in air in 1995, and one of the first experiments was done here in the LOA. You can even see the room where I just wrote all my thesis in. So if we look at the parameter of the plasma created, it's quite small, so it's diameter of 100 micrometers, and the distance over where you can observe this plasma can range from 1 millimeter, quite small, to hundreds of meters. And if we look at the plasma density, it's quite low ionization rate of several %. Here is a picture of one of these filaments. It's only centimeters long, and I wanted to show you a better one that I took, where you can see a plasma that are more 10 meters long. If you want to understand the process of the laser filamentation, it's as follows. It all is based on a nonlinear effect called Kerr effect, which focuses the laser as it propagates. So you see here the laser focusing, and when it gets an intensity high enough, it will create a plasma in air. This plasma will then defocus the laser, creating less plasma, so lessening the defocusing, until the focusing again prevails, and this cycle repeats over and over and over, creating our plasma channel. Then it is interesting to look at the time scale of all the process that I just spoke of. So first, there is a laser that has a duration from femtosecond to picosecond that will create a plasma. The heating of the plasma being small, its lifetime is up to the nanosecond time scale. But then I just told you that we wanted to use this plasma or this filamentation to guide discharge. And if you look at the propagation time of discharge, in our case it's meter-long discharge, it's in the order of the microsecond. So there is quite a contradiction between the 2 time scales. Thankfully, this plasma, after recombining, will heat the medium and result in an underdense hot gas channel that can guide the discharge. And moreover, there is possibly the presence of long-lived ion that can help this process. So then if we want to understand what's happening in the discharge, let's do a little model of the easiest discharge that we know, the Townsend discharge. So first, to this, we took two electrodes separated by a distance. Then we connect them and induce a difference of potential between them, creating an electric field. Then this electric field will interact with any electron present in the medium and accelerate it. And after a certain distance, this electron will interact with species in the medium, and if it has enough energy, it will induce an ionizing collision, creating two electrons. And then these two electrons will be accelerating again, creating more electrons. Then we need to take into account another effect, that is, when the energy is not high enough, the electron can be catched by the species in the medium, and so by electronic recombination. But if the electric field is high enough, more electrons are created at each cycle, and soon all the medium will be filled with electrons and a discharge is happening. From this model, we can have the expression of the breakdown voltage, which is the voltage required to induce such discharge. So this is quite a complex equation, but only two terms really matter for us. So if we just recall what I've just shown before, our two culprits for the guiding is either the underdense channel or the long-lived ion. So the underdense channel will interact with this term, so it will reduce the density, thus the breakdown voltage. And the long-lived ion will help by giving electrons that are easy to ionize, so reducing this value of energy of ionization. So we will create locally a channel where the breakdown voltage is lower than usual. And this will create what we call a guided discharge. So using this process, already two campaigns were done, trying to guide lightning. So the first one, man-made, is 2005, using the TerraMobile laser, with an energy of 270 millijoule and a repetition rate of 10 Hertz. You see it in its white container. And then another one was made in 2011 in Singapore, using the laser that pretty sure everyone here in the lab knows, the ENSTA-PARIS, with an energy of 300 millijoule and a repetition rate of 10 Hertz. However, these two campaigns failed to produce completely a real conclusion about if it's working or not. So we can ask what's new in our project. Well, this time the laser of the laser lightning rod system has an energy of 728 millijoules, so more energy. But moreover, the more important is that it has a repetition rate of 1 kilohertz. And why it's important? Because if one filament creates one underdense channel, we can start to wonder what's happening if we create an underdense channel before the previous one disappeared. And to this, we expect an accumulation effect, creating a stronger guiding. And so this effect of the repetition rate will be seen in two forms in this thesis. So first, at other repetition rate, we'll study the accumulation of the filament heating. So this will be done in the laser lightning rod project. But then there is another important aspect, is what's happening when you have the accumulation of the heating of consecutive guided discharge. And all of this is done in the framework of the EPAT3 project founded by the DGA. And the application is to try using this discharge to create a plasma antenna. All this study about the repetition rate can be seen in the laser system that I use during my thesis. So first we start with high energy with the ENSTA-Mobile with a repetition rate of only 10 Hertz. And then we move to the laser alpha-sound in cellular violet with an increased repetition rate of 100 Hertz, but only 15 millijoule. And then we can move to Salcorai with an energy up to 4 kilohertz, but an energy of only 2 millijoule. And then we have the laser with everything, I think. Yeah, the laser lightning rod system with a high energy and high repetition rate. So using this laser, we'll present you three parts in this presentation. So the first will be the study of the filamentation at high repetition rate. Then I will present you the study of the consecutive long-lived guided discharge. And then, of course, the laser lightning rod project. During my thesis, I made two additional work, one based on the superfilamentation, which is a particular filamentation regime which creates stronger filaments, and a more forward study of the long-distance filamentation during the laser lightning rod system. But for the sake of the time delay, we'll only focus on the three main parts here. So then start with filamentation at high repetition rate. So during this part, I will mainly speak about the filament characterization that was done with a setup that's called time-resolved transverse interferometry. It is as follows. So first we took our laser and we focus it through a lens to create or a filament or a plasma. And then we send perpendicular to it a nanosecond probe laser at different delay. And we look at how this probe is, how phase shift is induced on this probe laser by recording it with a wavefront sensor, giving us a 2D phase shift map. This is what the first iteration of the setup looked like when I started my thesis. And then I improved it a little to be able to move it around and even make it more rugged because it needed to survive the harsh condition of the experiment. So how do we interpret the 2D phase shift that we get from our sensor? Well, first we have our 2D phase shift map that is caused by the filamentation. However, at the time scale that we look, microsecond, the only effect that we need to take into account is the variation of density. So from this 2D phase shift measurement, we reconstruct a 3D density variation of the heated gas, so the underdense channel I was speaking about. And then what I will show is usually a cross-section near the middle of this underdense channel, where you will see the variation density. So previous setup was already described at the beginning of, just before my thesis. So first thing we've done is look at only one underdense channel and look at its temporal evolution. So we'll use an alpha-sound laser that I would just speak about earlier. And this is what we get. So if we look at different time delay, we see that initially there is a creation of one underdense channel with a reduction quite large of minus 60% of the density and a width that is similar to the 100 micrometers that I was talking about, that is the filamentation width. And then, if we look at width time, we can see that the channel width increase, the density variation decrease, and due to it being hot air is going upward. So then, we can try to model this evolution. So the easiest model is to look at the temperature in the underdense channel as an ambient temperature plus a variation due to the filamentation. Then we can model the temporal evolution of this variation. And then we can even calculate the evolution of the channel going up. And so, is it working? Yes, quite well. Because here is a comparison between the simulation and the measurement. And we see that we have quite a good match between the simulation in a full line and the measure in a circle. So then we have kind of understood what's happening with one filament. And we can move to what's happening at high repetition rate. So I will try first describe what we call the principle of the cumulative effect. That's happening at high repetition rate. So first, there is one laser pulses that create one underdense channel. Then, with time, this one will evolve. However, before it disappears, we create a second channel, and then we'll have the sum of both of them that will evolve together. And we repeat this cycle over and over and over, creating what we call the cumulative channel. So we try to characterize this cumulative effect by using a laser with a tunable repetition rate in Salcori. And this is the result that we get. So first, you see that at low repetition rate, 10 Hz, you see your typical singular underdense channel. However, we see that as we increase the repetition rate, there is an apparition of something that is way wider and more important than only one filament. That is the cumulative channel I was just speaking about. And we see that as we increase the repetition rate, the width of this channel increase, the density variation increase, and even the profile asymmetry increase. One other important aspect of this is that if we look at the temporal evolution of this cumulative channel, it is quite interesting. Here is a measurement made 100 microseconds after the last laser pulses. So you see here, this little part is the effect of the last laser pulses, and you see the cumulative channel. However, if you look at longer time scale, the last laser pulses effect disappeared, but the cumulative channel is still the same. So it's quite important to know that this cumulative channel is permanent over time. So then we can try to model this cumulative effect. And the easiest way is just to model the cumulative channel as a sum of all over channel. So is this simple model working? Yes, quite well, because if we compare again measurement and simulation, we see that we have quite a good agreement between the measurement and the simulation. So all of this was published last year in a paper fully describing all the setup and measurement. So then we are not just studying this cumulative channel for the sake of it. We wanted to use it on discharge. So what is the consequences on the breakdown voltage of discharge? So to characterize this, we use the same setup. So we create our filament, but this time we put 2 electrodes, one connected to a high voltage discharge generator that can be triggered. And this is what the result looks like. So you will see in the y-axis the breakdown voltage that is measured at different time. And if you want to understand what is the time scale, the time axis, it's at 0, it's the time at the laser pulses, and then we send high voltage pulse at different time. And we can move to scan the temporal evolution. It is important to note that the first 50 microseconds is too much affected by the last laser pulses and not the cumulative effect. So we will only focus on this part after 50 microseconds. And we see important thing is that first, that the reduction of the breakdown voltage increase with the repetition rate. And that this reduction is permanent over time. These are the 2 characteristics of our cumulative channel. So we can try to use the previous model that I just described to see if it can describe the reduction of the breakdown voltage. And this is the value that we get. So if we look at the expected breakdown voltage using our model and comparing to the measurement, we see that at low repetition rate, we have a quite good match. However, as we increase the repetition rate, we see that the measurement is less reduced than the expectation. Usually it's similar, it's the contrary. And so we can see that at high repetition rate, the reduction of the breakdown voltage is more important than expected. So we wanted to investigate this by repeating the same measurement in nitrogen. And here is the measurement. So here we see the measurement in nitrogen. We see again a permanent reduction that is increased with repetition rate. However, the reduction is less important than in air. So this time we can compare it again. And you see that, okay, this time it's matching quite well. So first we have a model based only on heating of the medium that is matching quite well with nitrogen, but not in air. So we can see that in air there is an additional accumulation of something that is not present in nitrogen. So for us, the best candidate is the long-lived ion I2 minus that I was just speaking at the beginning. So now we have kind of understood what's happening for the filamentation of high repetition rate. But to be sure that everyone remember, the main point is that if we at high repetition rate, there is the apparition of one cumulative underdamped channel. That is wider than a regular channel, deeper than a regular channel, asymmetric, and permanent over time. And moreover, in air, there is an additional effect of the repetition rate that we assign to the O2 minus ion. Then we can move to the other cumulative study, is the study of the consecutive long-lived guided discharge. So why do we focus on this topic? Is that first we start from one regular discharge, but this time, this discharge has quite a short lifetime. So the first thing is that we will increase the discharge, the lifetime of this discharge, and then we will guide successive discharge. All of this is done to create a permanent conductive channel. And this permanent conductive channel will be used to act as a plasma antenna, as I told you in the EPAT3 project. However, if someone has another idea, you can always discuss with me. So how do we do this? Well, we will use a Tesla coil to create Tesla coil guided discharge. So the setup is as follows. So first we have 2 electrodes separated by 83 centimeters. We send our ENSTA laser between them to create a filament. And to one of the electrodes, we connect the Tesla generator that was fabricated by Leonid. And this generator will induce a 300 kilovolt pulses that will be guided by the filament, thus creating a laser-guided discharge. So this was already described before my thesis. But right now we added a little something. A secondary generator that will inject current to the discharge to increase its lifetime. And this is what it looks like. So you see the laser here, and bam, that's the discharge. I remove the sound because you see me talking about over the video. So the first thing is that did we truly increase the lifetime of the discharge? Well, to characterize this, we made the measurement of the current. So first we start with the current of one discharge without any additional energy, so 0 joule. You see that the current is quite small, in the order of 50 microseconds. And this is what's happening when we add the energy. And you see that just with the current, we successfully increase the discharge time to millisecond time scale, and even up with the maximum energy to 3 milliseconds. So the first step is done. But then we will move to the consecutive discharge, but we need first to discuss how we will characterize them. And it will be done by the Schlieren imaging of the guided discharge. So the step is always the same at the beginning. So we focus a laser, we create our filament. Then we connect our two generator. And this time we send again a probe laser, but we will just send it through a spatial filter and record what's left with a high-speed camera. And this will allow us to see the evolution of the edge of the discharge at high speed. And here is what it looks like in real. So you see that the study zone will be mainly in the center of the discharge because we don't want to have any effect of the electrode. And here is an example of what you see. So this is the two edges of the discharge. And you see some parasitic light emitted by the discharge. But you see that with time, the radius increases. Well, then we'll use this setup to test how can we guide two guided discharge. And so first, we create one initial discharge, and we see that it's on the laser path, and it's quite straight. So this is a guided discharge as we expected. However, when you create a second discharge, something is happening, is that this one is not straight at all, and not even on the laser path. And it's not even reaching the second electrode. We don't have any current. So yeah, that's a bummer, but yeah, we can see that we can try to explain this because it's probably due to an effect of the first discharge that is preventing the guiding of the second one. But then, if we need to understand, again, we will need a model. So I developed a model based on the energy balance in the discharge. So you see, yeah, the gain mainly will be done by injected current, and the losses will be based on the thermal conductivity of air. And with this model, we too simulate the evolution of the radius of the discharge. And so is it matching with our measurement? Yes, quite good. So these are the measurement of the evolution of the discharge radius for different energy injected in the discharge. So the measures are in full line, and in several points you see the simulation. So it's matching quite well. And then we can even do this over a lower time scale to see, and again it's working, it's matching quite good. This model doesn't only give us the radius, but the evolution of the temperature of the discharge. This is what it looks like. Okay. So you see here that by increasing, okay, we have to do this with this. By injecting current, you see that we increase the time where the discharge temperature stay relevant and high, so might be conductive. And so we successfully increase the discharge, the time over the discharge stay hot, over to the millisecond time scale. But then we want to use this model, as I told you, to simulate the heating of the first discharge at the time of the second discharge. And we will compare it to what is supposed to guide the second discharge, the underdead channel. So we use the interferometer setup that I described in the first part, and we characterize this channel over the 83 centimeters. And if you look at the value, we have a maximum temperature variation of 208 Kelvin and an average value of 90 approximately Kelvin. And if we compare to the value of the remaining heat of the first discharge, we see that it's still 208 Kelvin. So the perturbation from the first discharge is higher than the variation of temperature that we want to use to guide. So this is why, perturbation being higher than the effect, we have no guiding possible. Well, the good thing is that it's not completely a dead end because we didn't stop here, and we try to induce an airflow to remove this heating of the first discharge because this is a thermal effect. So this is what the setups look like. So you see here the airflow that is just blowing air between the two electrodes. And did it work? So here we see that the first discharge, this is on the laser propagation path. And if we look at the second one, cool, this time it's working. So we have two guided discharge at 10 Hertz. So we can see that we successfully guided consecutive discharge at 10 Hertz. So the second part is done. So we can say in this part that we increase the lifetime of the discharge up to the millisecond time scale, and we observe a perturbation, find a way to remove it, and successfully guided consecutive discharge at 10 Hz. These two steps are quite big steps toward a permanent plasma antenna. But then I've presented you a lot of things that was done in the lab, so it's hard to move to the outside work. Oh, yeah, but first, let's not forget to publish our result. And so I will try to submit as soon as possible a paper describing what was done in this section. And so now that it's done, we can move to the laser lightning rod project. And so the main new thing in this project is the laser system that was developed by Trum Scientific Laser. So the energy is up to 720 millijoule with a repetition rate of 1 kilohertz and a pulse duration nearly 1 picosecond, depending on who measures it. And so this is what it looks like. So the first two parts are commercial parts, but the new part are this multipass amplifier, which have two stages, increasing the energy from 240 millijoule to 550, and then 800 millijoule. So after compression, what we get is a 720 millijoule, 1 picosecond laser pulses. Then we added two nonlinear crystals to create second harmonic of this wavelength at 130 and third harmonic. And we get quite good result with it, with energy of up to 300 millijoule in the second harmonic and more than 120 in the third harmonic. So then we get this laser and we wanted to test it before the official experiment. So from February 2020 to March 2021, the laser was installed in Orsay. It was installed in a tent to prevent it to have a lot of effect due to the temperature and due to the dust and all the difficult condition. And here you see the laser nice and cozy in the tent. Well, we get it by a little time lag because of the COVID, so we lost some time. However, we still resume the experiment and make the filament characterization of this laser over 130 meters to try to find the best parameter for the upcoming lightning experiment. So as an example, we characterize the presence of filament and over which length and where it started in different focusing regime. Using the interferometer setup of the first section, we made some measurements of the undernet channel. So again, you get the asymmetric profile of high repetition rate filamentation. And we even bring the Tesla and adapted it to be able to use it there, to observe guided discharge over 30 centimeters. But then we added to pack everything. And why packing? Because we need to go to Sentis. So what is Sentis? It's a mountain in Switzerland. But not any mountain, because it sits with lightning quite a lot. This is why there is a weather station recording and analyzing lightning run by the member of the LLR project of the École Polytechnique Fédérale de Lausanne. And so we went there. We took the cab. With the laser, it was a little more difficult, and some parts were even bring with helicopters. Then after everything was there, we needed to install all the setup and make everything work again. So this is the experimental setup that we went with as Sentis. So it's quite similar to the initial one. So you see the laser was set in a building inside its tent. Then it was sent outside, passing through a telescope, and then focused at the top of the tower, where it will create filament to guide lightning. And this is what it looks like in real. This installation took us 2.5 months, so that was quite long. But this laser was then operational from the 21st of July until the end of September. And during this period, 16 lightning flashes were recording hitting the tower. And 4 were in presence of the laser. So now it's time for the big question. Was the experiment success? I don't know for you, but the suspense is killing me, so we'll take a quick breath. Okay, then we will answer this question. So to do this, we use high-speed camera to image the propagation of the lightning. This is what an usual picture looks like. You will have to trust me on this one. This is the Sentis mountain. You see here the tower, and in white, the lightning propagation. And if we look at the temporal evolution, first for an event without laser. This is an example I've just shown. Then you see that with time, the lightning is going up, and in several directions, that it is branching. And then, as time goes on, It's even going in more random direction until going nearly everywhere. Then we can look at what's happening with laser. Immediately, it's quite interesting is that the lighting is going straight up without any branches. And as time goes on, it's still going up without any branches. Good. And then after a certain time, thus a certain distance of propagation, you see that it's starting to behave normally again, going to the left and even to the right and branching and everywhere. So here we already have some kind of guided lightning, but we need to be extra sure. So we took a picture of the laser path and overlaying it on the picture of the laser path. And this is what we get. So here you have the laser path, and here in white you have the lightning path. And so we can already see here that we have a guided lightning over 60 meters. So yes, we achieve victory. What? You want more? Oh. You're a tough crowd, but okay, let's continue. So first, this is only one picture. So we added a second one from different angle. To be extra sure, it's not a question of perspective. So this is a picture took from another mountain, and you see that even on this one, the lighting stay on the laser path. So that's good. So this is a right interpretation. Then we added another type of measurement, which is the detection of the sources, the high frequency sources that emit during the lighting propagation, with a detector that was set at the edge of the mountain. And here it's what a typical measurement looks like. So you have the vertical distance, the horizontal distance, and here in black, the tower. And in red is representing the laser path. And we see here all the dots of the sources that represent the lighting propagation. And the color scale represents the temporal evolution. So we see here that the lighting started from the tower, going to the left, made a circle, and went to the right. So then we can compare event without laser, the one that I just showed you, where the laser is going randomly in any way it wants, and an event with laser. And this time we can already see that it's completely different, and the lighting stays on the laser path, and is going directly up. To just convince you that I'm not just cherry picking the best example, okay, I might be a little. Here is more example. So here, event without laser. So you see that the lighting is going to the left, then more to the left, then this one is going immediately to the right. And here for the event with laser, each time we see that the lighting propagation stay on the laser path. But this is just a description. So we wanted to quantify this effect. So to do this, we calculate the distribution between the distance from the lightning path and the laser path at different heights from the top of the tower. And this is a result that we get. So for the first elevation range, we see that the average distance is quite reduced when we use a laser, a reduction of 37%. Then for the next 30 to 60 meters, we see that we have a similar difference and similar reduction. And then if we move to the last part, we see that the reduction is quite lower. And so it's only significant in the first two parts that were already quite long. So we have a guiding over 60 meters, which is coherent with the observation of the photo. Then we added another detection that is the X-ray emitted during the lighting propagation. So to do this, we used two X-ray detectors that were set in the same building as the laser that were looking up. Then here is the measurement. So first an event without laser. So you see that there is one X-ray burst emitted during the propagation. Then if we look at event with laser, we see that there is a lot more events that are recorded, an average of 4.3 X-ray bursts. So we can see that the laser increased the number of recorded X-ray bursts, and thus this X-ray burst being linked to the propagation, it is involved with the lighting propagation. Then we have another discussion that is kind of different. It's about the lightning polarity. So if you want to look, is that the lightning can have two different polarity. So a positive flashes mean that positive charges are in the cloud, and the lighting that is going up is negative. And then on the contrary, negative flashes mean negative charge in the cloud, and positive charges going up. And if we look at all the events recording 10 years prior to the campaign, we see that 84 are negative flashes, so nearly everything. And if we look during the LLA campaign, for the event without laser, we have kind of the same ratio. 82% of negative flashes. However, if we look at the event with laser, see that all events are positive. And that's not just random. We wanted to investigate this, and so we contacted Professor Kure of Uppsala University in Sweden. And he made a simulation and a model to tell us that if the laser initiates or promotes the initiation of any lightning, it will only promote positive events and not negative ones. And if we look at this model and this observation of us only having positive events, we can see that the laser is not only guiding, but even initiating lightning. So then we can move to the conclusion of this part. Not this conclusion. Okay, that's the right conclusion. So during the laser lightning rod campaign, we recorded 16 lightning flashes hitting the scientist tower, and 4 were in presence in the laser. And we demonstrate laser guiding of lightning over 60 meters. That is a first. And then we saw the promotion of positive lightning flashes. So all this was accepted and will be soon be published in a paper. So then we reach the conclusion of this talk. So we made 3 parts, so 3 conclusions. So the first, for the filamentation at high repetition rate, be sure to remember that there is an apparition of a cumulative, wide, permanent, underdense hot gas channel. For the consecutive long-lived guided discharge, that we increase the lifetime of the discharge up to the millisecond time scale, and guided successive discharge. And for the laser lighting rod project, that we made the first demonstration of laser guided lightning over 60 meters. Then there is always more to do. So let's look at some outlook. So for the first part, the next step will be to analyze more in detail the air chemistry and the long-lived ion, and how they behave at high repetition rate, and how they interact with discharge. For the second part, it will be to directly characterize the emission of this consecutive discharge in the radio frequency range. And then for the laser lightning rod, there is a lot to do, but the first step will be to study how the laser parameters affect the guiding, and moreover, it will be quite interesting to study different configurations that are closer to the final application of a laser lightning rod. So when we can move to the acknowledgement, because all this work was not done just by me, I was helped quite a lot. So first by the FELM team, that without them I will not have started this thesis and not even finished. So thank you all. Then I was not only working with the FELM team, but all the lab. So I had the chance to interact with a lot of you. And special thanks to the secretariat that always helping me when I need a plane ticket for like today. And the technical support team that made quite a lot of kind of electrode that helped me in my setup. And then, of course, the member of the laser lighting rod project that were with me during all this project. And all these people, of course, that I didn't say and that I met during my thesis. You know, the thesis that kind of started with a crazy idea and ended up making it a reality. So thank you all.